Hi everyone, I'm Kumara, and today I'm going to present our work, Video Conditioned Text Representations for Activity Recognition. This is a joint work with Anurag, Asha, and Michael. First, let's look at some key takeaways. We find that when adapting VLMs to video, it's not really a good idea to disregard text. We also observe that semantics in the form of text can be useful even without labels. For instance, categories such as human, object, or scene information can indeed be useful for activity recognition. Finally, we see that text can be more effective than visual embeddings, especially under limited supervision. The challenge that we are trying to address in this work is adapting image-VLMs to video. A generic framework would convert image embeddings to video, often keeping text unchanged. It would look something like this, where we have a video head plugged on top of standard image and text encoders, converting image embeddings to video embeddings. However, it's entirely optional to change text embeddings. If we look at some realizations of this video head, such as clip for clip, action clip, or clip hitchhikers, none of them change their text embeddings. If we look at something like EVL, it completely disregards text. Closest to ours is XClip, which updates both image and text embeddings. However, their focus on text embeddings is limited, and therefore the improvement that they see from updating text is also limited. In contrast, what we introduce is video conditioned text representations. It basically generates text specialized to each video. In other words, we are creating a more flexible latent space with a focus on text. Given text embeddings, now we are generating more text embeddings, each of them specialized for a given video. By doing so, now these video text embedding pairs has more flexibility to align in the latent space, creating better representations. Also, as a result, it can benefit from auxiliary semantics grounded on a given video. Any semantic concept given as a text can now be converted to video conditioned semantics, which can help guide this latent space. If we look at the core components of our model, our architecture looks like this. First, we have token boosting that creates a dedicated text token per given video and frame. For each text embedding, now we compute the affinity or similarity with a corresponding video frame embedding, and we weigh the text embeddings with the corresponding weight. By doing so, now we are creating text embeddings per frame. Next, we have cross-modal attention that allows text categories to attend to not only video embeddings, but also to other text embeddings. We simply concatenate all the visual and text embeddings and feed it through a self-attention. Finally, we have affinity reweighting that highlights or downplays text categories with updated affinities. It's similar to token boosting, but now the affinities are computed based on the updated video and video conditioned text embeddings. As for the learning objective, we have a standard loss formulation similar to CLIP, where we compute logits based on the affinity or similarity between video and video conditioned text. For this, we have labels. However, for auxiliary semantics, we don't have any video labels. To still learn from them, we try to predict activity classes based on these semantics. Here, instead of using visual embeddings, now we compute the affinities between text embeddings and the auxiliary embeddings, both of which are video conditioned. So how useful is our model? It's especially beneficial in low supervision settings such as zero shot or few shot. Here we show that we achieve significant improvements over models like XClip or XFlorence. It's basically because in these low supervision settings, it's easier to learn from semantics than from a few visual samples. It also works well in long-form recognition. If you would like to discuss more about our work, please visit us at Poster Session 4.